If the universe is truly endless, why does it feel like we live inside a bubble? Why do the farthest galaxies fade into a hard boundary we can't cross? Not because we run out of fuel, not because we run out of courage, but because the universe itself keeps moving the finish line. And here's the doubt that refuses to leave. If there is no edge, why does our view end? Why does the night not blaze with infinite light? Why do we see a horizon, a silent, curved limit, as if reality is telling us, you can look, but you will not pass. Tonight, we're not chasing aliens. We're not chasing a new planet. We're chasing something older. We're chasing the boundary of knowing. And we're asking the simplest question a human mind can form. The question that sounds like a child, but haunts the best physicists alive. What is beyond the edge of the universe? We know the universe has an observable limit, not because the universe ends there, but because light does. Light travels fast, faster than anything we can build, but it does not travel instantly. And the universe has a birthday. Roughly 13.8 billion years since the hot beginning we call the Big Bang. That means there's a natural expectation, a simple one. If light has been traveling for 13.8 billion years, we should see about 13.8 billion light years in every direction. But we don't. We see farther. We see a radius of the observable universe that reaches out to roughly 46 billion light years. So we know this much. The universe is old, light is finite, and what we can see is shaped by both. Here's the contradiction that makes the mind stop. How can something only 13.8 billion years old have an observable boundary more than 3 times that distance? It's not a trick of math. It's not a mistake in measurement. It's something stranger. Space itself has been stretching. While the light was on its way, the distance grew. So the edge of our view is not the edge of reality. It's the edge of what has had time to reach us. But that only sharpens the deeper problem. Even if the universe is infinite, we may be trapped in an island of visibility, a cosmic neighborhood bounded by horizons, not walls of stone, but walls of causality. There are regions so far away that even if they shine forever, their light may never arrive. And that is a hard thought for a human being, because we're not just asking what's far, we're asking what's forever unreachable. And once you accept that, another question grows in the dark. If there are places we will never see, how can we ever claim to understand the whole universe? Think of the universe like an ocean at night. You stand on the shore. You can see only as far as your lantern reaches, and only as far as the sea allows the light to travel. That limit is your particle horizon, the farthest distance from which light has had enough time to reach you since the beginning. But there is a second horizon, colder and more final, the event horizon of the expanding universe. This is not about the past, it's about the future. It's the distance beyond which, even if something flashes a beacon today, the expansion of space can keep that signal from ever getting here. And then there's the idea often described with the language of speed, the Hubble horizon, where recession becomes so extreme that space itself carries regions away faster than light can close the gap. Not because galaxies break the speed limit through space, but because space between us stretches. The result is the same to us. The universe can be endless and still keep most of itself hidden. And that is where the story begins. Because once you admit the horizons, you face a choice. Either the universe is larger than our senses can ever confirm, or we are missing something fundamental about what universe even means. The first hypothesis is the quiet one. It doesn't require new dimensions. It doesn't require parallel worlds. It requires only this. The universe continues beyond what we see, in more of the same. More galaxies, more voids, more time, more history, But the rules of light and expansion mean we inhabit a visible bubble, and the bubble is not centered on anything special. It's centered on us, because we are the observers. In this view, there is no true edge, only a limit to our access, and the most unsettling part is not the distance, it's the permanence. Because as the universe expands faster, some regions can drift beyond reach forever, even if they are real, even if they are brilliant, even if they are filled with life. Imagine that. Not empty darkness, but living, active galaxies, permanently cut off, like towns beyond a bridge that collapses. This hypothesis has a certain emotional cruelty. It says, reality can be real without being reachable. Truth can exist without ever becoming known. And yet, it fits what we already see. Expansion, redshift. A universe that makes distances grow while the light tries to cross them. But there's a problem. If the universe is simply more of the same, why do we see patterns that look too smooth on the larger scales? Why does the cosmic background, the afterglow, look so uniform across regions that should never have talked to each other early on? To explain that, science reaches for a deeper idea. The second hypothesis is a little more dramatic, but it's mainstream enough to live in textbooks. It's called cosmic inflation. The idea is that in the earliest instant, space expanded unbelievably fast, so fast that regions now far apart were once close enough to share heat and information. Then inflation ended, and the universe settled into the slower expansion we measure today. Inflation helps explain why the universe looks so smooth and flat on large scales. It explains why distant regions share similar background temperatures. It's one of the cleanest ways we have to make the early universe make sense. But inflation also whispers something else. If inflation happened once, it may have happened unevenly. It may have spawned regions of space-time that inflated into enormous domains. Domains beyond our horizon, beyond our maps, beyond our future reach. In some versions of inflation, it doesn't stop everywhere. It keeps going in places, like a fire that never fully goes out. And if that's true, then what we call the universe might be only one patch, one bubble in a much larger inflating reality, which brings us to the edge of a third hypothesis. Now we enter the territory where science touches philosophy, and the language becomes careful, because this is where hypotheses become expensive. This hypothesis says, beyond our observable universe is not just more galaxies. It may be other regions with different conditions, different physical constants, different histories, perhaps even different rules. Call it the multiverse if you want, but don't imagine it like science fiction portals and glittering gateways. Imagine it like weather, a vast atmospheric system where different climates exist far apart, and you happen to be born in one. In this view, what lies beyond is not a location you can travel to, but a region that is causally disconnected, not over there, but not connected to us. And it's here that the question becomes haunting. If there are other bubbles of reality beyond our horizon, how would we ever know? We can't point a telescope at outside. We can't send a probe beyond a boundary defined by causality. So is it science? Or is it storytelling? That depends on evidence. And evidence is the next chapter. If we truly want to test what lies beyond the edge of the universe, we don't look for a door. We don't expect a gateway, a rupture, or a visible boundary in space. We look for something far quieter. We look for a scar, a fingerprint, a leftover imprint etched into something we can still measure today. In cosmology, the most ancient and fragile relic we possess is not a galaxy, not a star, but light itself, the cosmic microwave background, this faint afterglow of the early universe is the oldest light that still reaches us. It is invisible to the naked eye, yet it surrounds us completely, arriving from every direction like a whisper left behind by creation itself. If something existed beyond our visible region, if our universe is only one bubble among others, if long ago our bubble brushed against another, or if cosmic inflation left behind subtle distortions, those events would not announce themselves clearly. They would not form pictures. They would not spell messages. They would appear as irregularities, a statistical bruise, a pattern that should not be there, but stubbornly is. That is what scientists search for in the cosmic microwave background. Unusual hot or cold regions that resist conventional explanations, large-scale alignments that seem too ordered to be random, and faint polarization patterns that hint at physics from the universe's earliest moments. Among the most sought-after signals are primordial gravitational waves, tiny ripples in space-time itself, generated when the universe was unimaginably young. If detected, they would allow us to see further back than light ever could, into an era forever hidden from telescopes. Beyond light, new messengers are slowly coming into focus. Gravitational waves do not travel through space. They are vibrations of space. Mapping a background of these waves could reveal events that occurred before the universe became transparent to light. Then there are neutrinos, ghost-like particles that pass effortlessly through stars, planets, and even our own bodies. A cosmic neutrino background is expected to exist, and detecting it cleanly would be like hearing a deeper, older layer of the universe's memory, one that light alone cannot carry. Another quiet signal waits in the radio spectrum, the 21-centimeter hydrogen line, a whisper from the era before the first stars fully ignited the cosmos. This signal could map the early structure of the universe in 3 dimensions, revealing how matter first gathered and where it did not. Even gravitational wave events themselves, known as standard sirens, can act as cosmic distance markers, helping refine our understanding of expansion, horizons, and the shape of space-time. And then there is the slow, patient work of mapping the universe's architecture, the cosmic web of filaments, the immense voids, the vast empty regions that look like holes torn into creation. If something beyond our horizon influences our universe even indirectly, its presence may reveal itself not through spectacle, but through imbalance, a mismatch that refuses to disappear. One observation could change everything. A confirmed imprint of inflation, a verified primordial gravitational wave background, a subtle sign that our universe once touched another. But for now, we are not there yet. We have hints. We have tensions between measurements. We have competing interpretations. What we do not have is closure. And perhaps that too is part of the story. So what is beyond the edge of the universe? Maybe it's simply more universe, more galaxies beyond our light, more suns rising in places we will never see. Maybe it's a reality shaped by inflation, a cosmos so large that our entire visible sky is only a small province. Or maybe the very word beyond is a trap, because the universe may not have an edge the way our minds imagine edges at all. And that might be the hardest truth for us to accept. Not that the universe is empty, but that it is too full, too vast, too patient, too indifferent to our need for closure. We are creatures who measure with light, who think in lifetimes, who want the universe to fit inside a story with a beginning and an ending. But the cosmos doesn't promise that. It offers us horizons, and then it offers us something else. The ability to keep asking anyway. And that's what we do here, together, at Deep Space Inquiry. We take the questions that don't let go, and we sit with them long enough to hear what they're really saying. Because even if the universe never gives us a final boundary, the search itself changes who we are. Sometimes the greatest frontier isn't what we will reach. It's what we will never stop trying to understand.